All right, hello there, everyone. So this video is about Project 2 in my course CIS351. It deals with the first compilers project. And I wanted to look at some test programs and explain the various IRs. Okay, so this project involves us translating, we're following Jeremy Seek's Essentials of Compilation book, and we're in chapter 2. So we're following chapter 2 here, and this is the list of passes, and this mirrors, so each pass, so the input here is R1, so that's R1, huh? So the input pass looks like, basically it's a program followed by an R1 expression, huh? Okay, so as an example, the simplest program we can write is just a constant. So for example, here I've got program wrapped of 42. 42 by itself is not sufficient, because if we look at the IRs here, I have to have this program thing that's kind of wrapping it. Sort of like the main expression. Okay, so if we look at this one, if we load it up, so I ran the debug server, and I loaded up R0 native 1. Now, the outputs won't change because the program generates a constant, so doesn't read any input, so it's going to be invariant under the different choice of inputs. So let's just talk a little bit about how to read the little output on the right here. By the way, I can go and run my solution here. And I can see the input to this pass is program 42. This pass, it does a few things. One of the things is that it will make variable names unique. So if you use a variable name more than once, or if you rebind a variable, for example, it will make it so that every binding is to a syntactically distinct variable. So when you've got a variable, you can precisely identify its binding site in the program. But also, in this case, there's nothing to change, right? So maybe we'll make this a little bit bigger. In this case, it's just 42. No variables at all. Maybe if I was using a variable here, this pass would do something more interesting. But in this case, all we're doing is we're wrapping program, and then we're adding just this empty list right here. Now, this is just a little bit arbitrary, but it's just how it is for this part of the project. Eventually, we're going to put some more metadata here. So our program is going to be something like program, metadata about the program, and then it's going to be maybe something like an expression or something like that. It'll get more complex in the future projects. The goal of ANF conversion is to basically make complex expressions simpler. So in this case here, program 42, we can't really see much interesting, right? Because 42 is just a literal value. And in this case, this pass ANF convert is not really going to do anything, which is one kind of thing that's a little bit nice about this project, is that you can start it without, you can start it by just punting and not doing stuff. Here, we get to explicate control. This is a really good example of something that's going on here. This pass, explicate control, is the first pass that lowers things from, in this case, at the source language R1, after uniqueify and after remove complex. All of the things that were kind of flowing through those passes, they still have this general structure. Program, some metadata, and then an expression. But after explicate control, suddenly this thing changes substantially. So it's going to change now to being a hash table. It's going to be a hash that's going to map, in this case, there's only one symbol, and it's going to be main. And we're going to map that to a sequence of commands. Okay, so let's go look at that. So a C0 program, the thing that gets emitted by explicate control, it's programmed with some info, which in this case is just empty. and it's always going to be empty in this pass. And then it's going to be a hash table called blocks, and the hash we have to have this key, which I'm going to put here as entry symbol. This is actually defined in system.rkt. It's main. But it's a little bit nice to abstract this kind of stuff by, making making some sort of a function for it. In this case, it's something called a parameter. But you can call it as a function with 0 arguments, and it will give you that value. Now, what are we asserting? So we're saying basically this is a hash table. It has to have a key named main. That's one thing that we're saying right here. We're saying, okay, blocks has to be a hash table, has to have a key named main, and associated with that key has to be something called a C0 sequence. And that's basically a sequence expression. So we're saying basically that the program is now a hash table mapping a single block name to a sequence of, in this case, it's going to be either sequence of assignments followed by a rest, or it's going to be a return. And so if you think about this a little bit, you basically get sequence of assign, sequence of assign, sequence of assign, sequence of assign. Eventually you get a return. So it's basically a straight line expression. And we would traditionally call this a basic block. Now on the right-hand side of an assignment has to be this C0 RHS. Basically it has to be simple. It can either be a literal, a symbol, it can be a call to read, it can be negative, where you're binding an atom, it can be plus, where you're adding both atoms. So that's the output of explicate control. Uncover locals, I actually give you this pass. If you look at compile starter, here's what uncover locals does. It calls H on the single block in the program, which you can get by calling href of E on entry symbol. There's only one block in this program. In general, our programs are going to have more blocks. Like, for example, in the next project, we're going to have multiple blocks because we're going to have branching control flow. In this case, it's simple. We've only got a single block to work with. And so what we're going to do is we're going to call this function H on it. And then H, all it does is it just walks over every variable in the block and it adds it to a set. And then it calls itself here. So it calls itself recursively. Eventually it returns the empty set. Then it does set add and basically adds all the variables that are ever appearing on the left-hand side of an assignment. That's what uncover locals does. Now that pass is not too interesting. I don't think it's something you need to code up for yourself. So I put it down here. So that's what locals program is. That's the output of uncover locals. And again, you don't need to do that. It's already done for you. Select instructions is one that you do have to do. So the output of, now here, we associated main with basically this C0 sequence, which is basically seek, 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 followed by return. All right, actually, if you look at this C0 seek, it actually looks a little bit like a list, right? It should look, I mean, it is a list, so it should look like a list. But what I mean by that is that a list in Racket is either the empty list or it's cons of something followed by another list. And that's what it is here too. It's either return, which is the end of the list, right? You have to have at least the, every basic block, basically in this case, we're going to say has to end with a return. And then we're going to have sequences of these things. And we're going to generalize these to be more interesting in the next assignment. Okay. But here, after select instructions, we're still going to have the same basic representation. We're still going to have a main points at, main points at, now it's going to be a list of instructions. And so what I'm doing here is I'm saying that if I take href of blocks and the entry symbol, that had better give me a list In fact, this is a little bit sloppy. The starter code should also probably be checking that this thing is a list before it calls andmap on it, because if it's not a list, that will break. So that's a little bit sloppy on the predicates part. I'll have to fix that for next time. But in any case, it's checking that every element, basically that this block is a list of instr vars ha. So those are instructions which can contain variables. And here are the possible instructions. They can be move queue, add queue, neg queue, push queue, pop queue, call queue, or rec queue. But in this case, at this level of the IR, if we go look, in this case, we don't have registers yet. We still are going to have variables. And so we're going to let our operands here be either immediates, which means constants. That's what imha is. It's just literals, integer literals. It's going to be a reference to a register, which in some cases we might have. I don't actually remember if my implementation does or not. Or we can have varhas. And we're not going to say how varhas are going to be implemented yet. That's going to be after assign homes. That's the next pass we're doing. The result of assign homes should make it so that all of our references are either to, so now it's going to be instructions. Instructions are going to look the same. So if we go look here, I'm saying, for example, move queue, immediate 42 into racks. In this case, I think I'm going to get stuck pretty quickly because I'm not going to have enough interesting things to talk about. So let me sketch another program, but let's just look at this first one. And so to say, eventually we're going to have variables. In this case, we don't have any variables. It's just a constant. So this pass is uninteresting. In fact, this is why you could probably go implement this right now. And then let's see, patch instructions is going to take care of some tricky instructions that we might get as the result of doing stack allocated variables. Prelude and conclusion. This is going to stick in basically some code for doing the, basically doing the prelude, which is the first few instructions in the function. Typically you push the base pointer, move the stack pointer into the base pointer, and then subtract the requisite amount of stack space. In this case, there are no variables. So we're emitting this instruction add 0 to the base pointer, which is basically a no op, right? It's going to be an instruction that the machine executes, but nothing will change. And then we've got our code here. We've got our return value here. And there we go. And then eventually render x86 results in the actual assembly program. And I believe I have also written, so dump x86-64 is the code that will do this. And this is mostly written for you. There's some code that generates the beginning to say which which symbol should be globalized. There's an inclusion of some externs which generate these definitions for runtime.c, because we're linking with a single C file, runtime.c, which includes the definitions of these two functions. So they need to be externed. And then it also, very crucially, uses RTSym to make symbols specific to the architecture we're on. In this case, I'm compiling on a Mac, and so I need to use underscore, I need to use underscores before my symbol names that I export. So for example, main, read at 64, print at 64. I handle that by using RTSym. Now, I say down here, I kind of sketch out in render instruction a few cases. I sketch the case for call queue and for leave. But it's your job to generate the rest of the cases for things like move, add, push, I believe. And then you might also consider using a helper called render op to render these operators. Okay, so let's look at another program. So the next program we might look at is this R02. So let's load that up. Now here, R02, I'm taking the addition of 5 plus 3 and minus of 2 plus read. So the passes are going to get more interesting. Let's look at them. First of all, the output of uniqueify, no difference in this case, except for adding on this extra empty list, which is just required by the predicate. So you just add an empty list there. Eventually, we're going to stick some more metadata there. So this is just anticipating that. But then no variables. So nothing happens in this pass. But a lot happens in this pass. So this pass, ANF convert, is basically going to do this thing of walking over the more complex instructions, binding them and generating them to these intermediate lets. So here I'm saying take the result of take the result of 5 plus 3, bind that to this new symbol plus 5979. Then call read, bind that to read 5980. Then call bind, so build this intermediate result right here and bind it to plus 5981. Also, when I have a symbol that starts with plus, Racket's also going to print out the little pipes in front of it. That's just a piece of trivia. You can use GenSim to get new variables for these names when you're generating them yourself. And we'll talk more about how to code up this pass in class. But just showing you now that here, basically this ANF convert pass is going to take this complex program, and it, of course, the output is also relatively complex in terms of, number of lines. But it's all of the functions in the program have simple arguments now. They're either variable names or they're immediate values or literal values. Okay, so now explicate control is then going to take the output of this ANF convert pass, and it's going to convert it to this format we talked about before, which is basically a hash table with a single key, main, and the value associated with that key is going to be a list of assignments ending in a return. So we can see here, it's seek assign this. So here we translated this thing here into an assign. And then down here, this next let now becomes an assign to a read. So the right-hand side here has this kind of simple form. We're just going to walk over these nested lets and transform them and kind of flatten them out into a sequence. And at the end here, we're going to return this value that we computed as a result of all these other expressions. After uncover locals, I now have the set of local variables that I'm using. So that pass just walks over all the things here, pulls out the local variables. This is going to be used, by the way, later when you do assign homes, because basically what you're going to do is you're going to take this set of local variables and you're going to count the number of elements in that set. Then you multiply it by 8. That's how many bytes you need to subtract from RSP, except there's one thing, which is that you need to ensure 16-byte alignment. So that's something we will talk about during class a little bit as well. And I have some words to talk about that. So then the select instruction pass is going to turn each of these things into things that actually look like assembly. So now instead of having these seek, so see how it's like seek, 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 return. Now we just flatten it truly into a list of these instructions, except we can also use variables. All right, so here, we can talk about how we would do this in class, but this is implementing just all the various pieces of things. Like, for example, here to implement this assign plus 5984 to be plus a 53, we've done two things. First, we've moved 5 into register racks. We're assuming that racks is free. We're just trashing it. We don't care what its value was before. Now we're going to take the output of, now we're going to add 3 to that register, which is going to leave the result in racks. But we want the result to be in plus 5984. So now we're going to do a move Q of register racks to var 5984. All right, so that's what's happening in that pass. Assign homes then is going to take these usages of variables and is going to turn them into dereferences relative to RBP. So at the beginning of the code, well, we don't see it here because it gets inserted at the end at the result of prelude and conclusion. But we're going to initialize the RBP to be the base pointer. We're going to subtract the requisite amount of space from the stack pointer. And now the first local variable is located at -8 RBP. The second local variable is located at -16 decimal RBP, -10 hex, right? The third local variable is at -24 RBP, and then -32 for the fourth. 0 of RBP would be kind of the variables from the preceding frame, right? And so, okay. Anyway, just to kind of jump back. So here we've got assign homes. And that's going to turn these usages of variables into stack references. Let's see, are there any places though where we have deref occurring twice? Because if we do, that's bad. We talked about in class the fact that generally assembly instructions, they can only take one of their arguments to be a reference to memory, right? If you want to move memory around, if you want to move something from, let's say, the stack to another place on the stack, you can't just do that by saying move, and then give a pointer and then to another pointer. That's not allowed, right? You have to pull it into a register first. That's a kind of a fundamental way we generally design CPUs. And so that's what's going to be taken care of in this patch instructions. But in this case, I don't think there were any problematic instructions. So basically what this pass does is it just looks through all the instructions and sees, are there any problematic places where I would have, both of my operands being dereferences. And in the event that there is, basically what you use is you use a temporary register that you assume is just available. So maybe like RCX. You temporarily move one of the results into that. That's kind of the trick. There's more about it in the book. Then prelude and conclusion adds on the code to basically begin the statement. So first we push RBP. We always do that and move SP into RBP. That initializes the base pointer. Now we're basically allocating 48 bytes on the stack here. One really kind of a little bit of a tricky thing that we'll need to talk about more potentially in class is that notice how we use -40. We actually we never use -48. So the question might be, why are we allocating 48 bytes of space when we only need 40? So it turns out there's actually kind of a quite tricky reason why this is the case. So this is the reason. When you allocate space, when you call a function in this ABI, sort of the system, sort of the 64-bit ABIs that we're using in class, the stack needs to be 16-byte aligned. Now, so 48 divided by 16 is 3. So we're allocating 48 bytes of space. And so we're putting that on, and we need to make sure that whenever we call a function, the stack is aligned. So here, upon entry to this function, the assumption is the stack was 16 byte aligned, which is the convention, meaning that RSP has to be at a multiple of 16. So now a question that you should probably, at least that I would be asking is basically this. Here, we subtract 8 from the stack by pushing reg RBP. And remember, when we push, the stack grows down. This is a key thing. Whenever you push on the stack, you're actually subtracting from RSP on basically every modern machine. For various reasons we're not going to talk about, for example, but now the question is, why do we subtract 48, or which equivalently is add immediate of negative 48? Why do you subtract negative 48? Because 48 is divisible by 16, but then we've got this 8 bytes here. So then at this call to read int 64, how are we 16 byte aligned? Because this is 16 byte aligned, but this is another 8 bytes. So we shouldn't be 16 byte aligned, right? But the answer is this. It's that when you call, that call instruction pushes a return address onto the stack. And so that's where the other 8 bytes is coming from. And this was something that to me was very confusing when I was first thinking about it. Okay. Let's look maybe at one more program here. Let's look maybe at R11. Okay. Let's run my output. Okay, so here, this is going to be a place where Uniquify actually happens. So let's check this out. Here I've got a let x be 2 in the body, let x be x, and in the body, let x be x, and then x. So here, this x refers to this x refers to this x here, and this s refers to this x. Eventually, it should all be 2. But in this case, Uniquify will actually do something interesting, because we will rebind this new x right here, because this is a syntactically distinct x from this x and from this x. So now we bind this x5989 to distinguish it from this x right here. The way that I wrote the code, you only allocate when you haven't seen the variable sort of so far. And then right here, this is a new x. So this is x5990, and that's bound to this one. And then when we see this x right here, we can immediately see, oh, it corresponds to this x because it's 5990 rather than x right here. So this is a case where Uniquify actually does something. Now, otherwise, we're not going to do anything. In this case, ANF conversion does nothing because the program is already ANF converted. There's nothing complex to break down. Explicate control is going to turn it into a bunch of sequences, right? It's going to assign x to be 2, assign x591 to be x, assign x5992 to be 5991, and then return x5992. So let's see if that's the case. Assign x to be 2, yes, so that's this one right here. And then at the end of a seek is a seek. That's just how the type is written out. I'm just following the type in Dr. Jeremy Seek's book. And so, I'm trying to be as compatible with them as possible, and this is just what he did. So this is how he writes little sequences in this C0IR, I believe it's called. And so we're assigning x to be 2, and then we're assigning 5991 to be x, and then 5992 to be 5991, then returning 5992. Great, perfect. Okay, and then uncover locals does its thing, select instructions, turns these into, so now I'm going to move immediate 2 into x. I'm going to move x into var 5991, move var 5991 into var 5992, move var 5992 into rag rex, since that's the returning value, right? So that's the result of the fact that the answer for the program is left in racks, and then at the end, I think I actually should have said this probably earlier, but part of prelude and conclusion is that they move racks into RDI to then call print int64, because in this language you can't just print whenever. There's no explicit print command in this language at all, or sorry, print expression. Or so in this case, it's just that whatever the value or whatever the program returns is printed, and so that doesn't actually show up, except for the fact that we assume that the value will get, I think we assume that the value is stuffed in racks. And then we move racks into RDI, and that's just how my prelude and conclusion work. At least that's the way I set it up. Okay, any other cases worth talking about? Maybe here we can see another case where, okay, so how does assign homes work? Well, basically what it's going to do, it's going to figure out how much space on the stack do I need. And also notice that the output here of assign homes, instead of this set here, which is just a set of variables that are used by the program, we're going to have a hash of each of the variables to its location on the stack relative to the base pointer at the beginning of the function. And we're assuming that RSP at the beginning of the function moved into RBP after we've pushed it. So here, to figure out where 24 is, we just dereference RBP by 24, and then we assume that RBP is going to stay the same throughout the function, and that's a common assumption, in many compilers. There are some compilers that try to use RBP as a general purpose register and reuse the stack pointer and just not rely on RBP, but that's kind of a more complicated thing to do, so we're not going to do it right now, at least. Okay, I think that's really all there is to say. It might be nice to see a case where we see maybe some instructions. So here's maybe a bigger one. Sorry, what I mean is places where the patch instructions pass actually would matter. Okay, so here, this is a good example. So this is an example of an offensive instruction that we could not actually omit. So here I've got a move of a, now when I write dref reg RBP -8 in x86 assembly, that's like -8 RBP. This is what it looks like in gas assembly. So when you see dref reg RBP -8, you should think eventually it's going to get translated to this in the render x86 pass. But you can't move Q, so you can't move Q -8 RBP to -16 RBP. Not allowed. But what can you do instead? If you assume there's a free register, let's call it RCX in this case. So we're just going to use that one. Maybe we call it RCX. Now we can move Q RCX into -16 RBP. So things like this are going to get translated into these expanded instructions. Let's see which register I use later on. So here, yeah, so I use racks. I assume, there's no reason I can't use racks, because at the end of the day, I'm rewriting everything back to the stack. And so I've always got racks available, which is the beauty of just not doing register allocation and kind of punting. So it's going to be more interesting later on, I suppose, if you implement register allocation. I'm going to make that a final project this year. But here we can see where this code that was otherwise trying to ferry data between RBP -8 and RBP -6, we expand it into these two instructions. So that's all patch instructions does. It finds patterns like that and it replaces them. Prelude and conclusion then allocates the necessary space on the stack. So the output here is push RBP, move RSP into RBP, very, very common. Then we calculate and figure out how much we need to subtract from the stack pointer, and then we're good. We got our code. All right, so that's pretty much all I have to say tonight. And but I appreciate you listening on, and hopefully this helps a little bit with your project. So thank you.